Good evening, everyone, and welcome to our comprehensive presentation on brass alloys. I am Roshan Jawad Zafir, and I'll be covering the fundamental properties and introduction to what brass actually is. And not just me, I am here with four of my other group members. We have Tamid, we have Nur Muhammad Adam bin Nasir, and we have Muhammad Amirul Hakim bin Abdul Razak, and we have Kumarasan A.L. Mokan. And we might not notice, but we do have brass in our everyday lives, starting from your bathroom all the way to the huge naval vessels that dominate the seashores. Um, and brass is an alloy, as you might see in the infographic that we have here, and it's an alloy of copper and zinc, two of the elements that are present in the periodic table. And you might ask, what's brass? And as I just said, it's a zinc, copper, or copper zinc alloy. It's non ferrous red metal made mostly of copper and zinc, and different amounts of copper and zinc can achieve various mechanical or electrical quantities that engineers want to achieve while they are working with brass. And when talking of the structure, brass has a crystal structure which is FCC, and that applies for alpha brass, and BCC, which applies for beta brass. And you can see the key properties that we have attached for brass, and one of these is excellent corrosion resistance, which makes brass a very good material to be used for bathroom fittings and pipes and whatnot. And some of the applications of brass includes musical instruments, plumbing, fittings, ammunition, marine hardware, and so on. To understand how brass shifts its properties, we have a phase diagram which will be explained by my teammate later on in the video. But for now, you can see that in alpha phase, when it's FCC, we have 0 to 37% or a low composition of zinc, which makes the material ductile. At the same time, we have beta phase, which is BCC, which is about 37 to 50% of zinc, and it makes the alloy more strong. At the same time, we have six different compositions to analyze, which again will be explained by my teammates later on in the video.
Assalamualaikum and good day everyone. Before I go into the detail of zinc composition in brass, let's briefly talk about why this composition is metal. Brass, as many of us know, is an important alloy mainly made from copper and zinc. By adjusting the amount of zinc, we can significantly change its properties like strength, ductility, and how easily it can be shaped or formed. This is why different types of brass are used in so many everyday items, from jewelry and musical instrument to marine hardware and structural components. So, let's start with low zinc composition, which include 5%, 50%, and 30% of zinc. At 5% of zinc, also known as red brass, solidification occurs from liquid to liquid plus alpha phase, and finally to a full alpha phase. The microstructure consists of single alpha phase grains that are quite uniform. This gives the alloy high ductility and excellent cold workability, making it perfect for decoration item and jewelry, where easy shaping and fine detailing are important. For the second part, which is 15% zinc, known as cartridge brass, the solidification process is very similar, liquid to liquid plus alpha and then to alpha phase, but here the microstructure is strengthened through a solid solution strengthening, while still remaining a single alpha phase. This result is a good balance between strength and ductility. Because of this balance properties, it's widely used in ammunition cases and lamp fixtures which require forming but also strength. And moving up to a 30% zinc, which is often called as 7/30 brass. We still have the single alpha phase structure, but now they offer higher strength. This composition is especially excellent for deep drawing processes, making it ideal for musical instrument and architectural hardware where both strength and formability are important. As shown in the graph on the slide, as the zinc content increase from low to around 30%, we see the strengthening of the alloy rising while ductility gradually. Now, on the next slide, let's move on the high composition, which include 37%, 40%, and 45% of zinc. So, at first, at 37% zinc, this composition sits right at the alpha-beta phase boundary. The microstructure mainly consists of the alpha phase, with beta phase forming at grain boundaries. This is a transition point where properties start to shift and is often used for specialized high-strength application. And next is 40% of zinc, also known as Moon's metal. Solidification involves both beta and alpha phases. The final microstructure has about 50% has about 50% alpha and 50% beta at around 600 Celsius. This mixture provides higher strength but also reduced activity. And it's suitable for application like marine propeller and architectural elements where higher strength is needed to withstand mechanical stress. And finally, at 45% zinc, which are known as high zinc brass, there's a significant beta phase content after solidification. This gives the alloy high strength but limited cold workability. As a result, it mainly used in the structural component and hot work product where strength is more critical than ease of forming. On the right slide, you can see micrograph that illustrate how the beta phase appear and increase with zinc content and cooling. So for me, in summary, increasing zinc content generally increase the strength of brass, but reduce the ductility and cold workability. This explains why low brasses are preferred for decoration, easily formed item, while high zinc brasses are better suitable for structural and high strength application. Thank you.
So now I will explain a phase calculation example using the lever rule for brass. This example is at 600 degrees Celsius with 40% of zinc composition. From the phase diagram, we can estimate that the alpha phase has around 30% of zinc, while the beta phase has about 50% of zinc, and the overall composition is about 40% of zinc. By applying the lever rule, we can calculate that the alpha phase has about 50%, as well as for the beta phase it's about 50%. This means the alloy has equal amount of both phases. In terms of properties, this gives us a balance between ductility from the alpha phase and the strength from the beta phase, which is very useful in many applications of brass. Okay, now let's look at the different methods to improve the properties of brass. There are three main approaches: heat treatment, mechanical processing, and alloying additions. First, we have heat treatment. Annealing at temperature between 400 degrees Celsius to 700 degrees Celsius helps restore ductility and relieve internal stresses caused by prior processing. Recrystallization removes the effects of wood hardening, making the material easier to shape again. And solution treatment is also used to even out the composition, especially when multiple elements are involved. Next is mechanical processing. Cold working significantly increases the strength of brass by up to 2 to 3 times, but it also reduces ductility. Hot working, on the other hand, helps shape the material while maintaining its ductility, making it easier to form complex parts. Deep drawing. Deep drawing is the specialized forming method that works particularly well for alpha brass, which also has high ductility. Finally, we can enhance brass by adding alloying elements. Adding a small amount of lead, 0.5% to 3%, improves mechanicability, which is why it's used in free cutting brass. Tin, around 1%, is added to improve the corrosion resistance, especially in admirably brass, which is commonly used in marine environments. Aluminium is about 2 to 3%, helps to increase both strength and resistance to corrosion, making the alloy more durable.
Hello everyone, I'm Mohammad Hamid Rashid and today I will be presenting the industrial application and the advantages and some limitations of treated brass. Brass application spans virtually over every industry due to its unique combination of properties. For example, in the music industry, the acoustic properties and corrosion resistance makes brass ideal for wind instruments. The 70% copper content provides the perfect balance of resonance and durability. Um, Next is in the marine application. Naval brass resists seawater corrosion while maintaining strength. Ship propellers, portholes, and deck hardware rely on brass. Since when used in the ship, the seawater can cause corrosion to different type of element, but brass is corrosion resistant, so as a result, it can be used in marine applications. Next are plumbing and architecture. The antimicrobial properties of brass makes it perfect for door handles, for faucets, fixtures in hospitals and public buildings. Also, it can be used in for ammunitions as it has high strength, ductility, and reloadability. For a case study, we can take a French hornbill. Before Cold War, it is hard and bitter. Um, then we do the treatment of annealing and deep drawing, which makes it formable and have excellent acoustic resonance. Now for the advantages and future applications of brass. The advantages of brass, for example, are it has high strength, ductility combination, superior corrosion resistance, attractive golden appearance, wide property range through compression, composition control, excellent workability, natural antimicrobial property. These are some of the advantages of brass. But there are also some limitations of it. For example, limited high temperature use. Since brass has a really low melting point, as a result, mm, when used in high temperature condition, um, it can be more ductile, so it can melt when worked in high temperature. For this, the solution may be to consider using other copper alloys. Season cracking. For example, in boats, the hull, if it is made out of brass and if it is left out in the cold for a long period of time, then cracks form on the hull of the boat. For this, the solution may be self-relief annealing. Next is the future application. The future applications of brass may be antimicrobial surfaces, for example, in the hospitals and public spaces, since it has um, antimicrobial conditions. So, when used in public spaces where a lot of people has contact with, the bacteria, viruses, whatever it may be, cannot be contaminated into the surface. Advanced manufacturing, for example, like 3D printing, it is since it can be since it has excellent workability, so we can use it in 3D printing. Sustainable recycling, it is 100% recyclable. Smart alloys with controlled properties. So if we input different type of alloys in brass, so we can control the properties it may have, so that we can cater it into our desired needs. Thank you. That's all from me.
To summarize, brass is a copper-zinc alloy with 5% to 45% zinc, offering tunable properties through composition control. Alpha phase brass with up to 37% zinc are ductile and great for cold working. Meanwhile, alpha plus beta brass offer higher resistance and suitable for hot working. Using the copper zinc phase diagram and lever rule, we can predict phase composition and optimize brass for specific need. Beyond composition, treatment like annealing, cold working, and alloying with elements like lead or tin improve strength, machinability, and corrosion resistance. From musical instrument and marine hardware to plumbing and architecture, brass remains essential across industry due to its strength, corrosion resistance, and aesthetic appeal. Its versatility and recyclability ensure it will continue to be a vital material in the future. Below is all the references that we have used to make this research.
So that was it. Thank you to all who have watched this video until the end, and a bigger thank you to all my teammates who have put in their efforts to share some knowledge about brass. I have explored how brass combines copper and zinc to create one of the most versatile alloys. From the phase diagram, we understood how zinc content controls microstructure and properties. Calculations like the ones that were shown help us predict and optimize alloy compositions for specific applications in certain fields. Various treatment methods allow us to enhance or modify the properties for demanding service conditions. And last but not least, real world applications demonstrate brass continued importance across all industries. And whether it's the trumpet in a symphony, the propeller on a ship, or the doorknob you turn every day, brass continues to be an essential material in our modern world. And hence, I would like to thank you for joining us in exploring the fascinating world of brass alloys, and I hope you enjoyed the entirety of the video. Thank you, everyone.